All right, thank you for coming, and this lecture is available for recording. Just want to tell that for those that are watching it later on. So welcome to class. Thank you all for coming one more time. Let's start with some announcements. Today is the 10th. Did you guys have a good rest day? I guess they call it rest day. Very good. More people are showing up. That's good. So let's see. The important thing I want to tell you guys is test 1 is next Monday. Okay, you still come to class. Everything's going to be done through computer. So there's a multiple choice portion of the exam. So let me just tell you that the multiple choice portion of the exam will be open Monday, I think 12 a.m. to 12 p.m. So you'll have the whole day, and you'll have 2.5 hours. If you have an internet issue, like I told you before, I have terrible internet. Actually, it affected my son's class. He has a speech class. He didn't have good internet. So just email me or text me, and I'm sure we can figure something out. Anyways, the multiple choice portion is about 20 to 25 questions this Monday. And then there's a problem set, which I believe should be available Friday. So you can work on those problems over the weekend. And then the problem set show all your work as much as possible to get partial credit. Problem set open on Friday. That is this Friday. And you want to turn that in also with your exam. When I say turn in, we'll upload it. Okay, we're still in a situation where a lot of athletes still cannot come to class. I know I spoke to one of them a couple of last weekend, last Saturday. So you want to turn that in along with the multiple choice of your exam. Okay, prior to this pandemic, I have, as part of my system, the quizzes being due always the same day as the exam. So in this particular case, you'll upload the quiz. Okay, make sure it's good work that we can grade for a partial credit. I'm not grading these. My assistant grades them. So make sure you turn that into Canvas by the 15th. So those are the two big things. Also, their study guide is available on Canvas, so this will tell you, sort of pinpoint what to study for. So study guide on Canvas. So that's what you want to look for on the weekend, over the weekend, as you prepare for your studies for this first exam. And I'll have a review class Friday. Hopefully I'll finish chapter 12 today. I'll also have office hours from 5 p.m. to 8 p.m. the night before the exam. So 5 p.m. to 8 p.m. I'll be in my office. Actually, I'll be in my home, and we'll have Zoom office hours. You do not have to attend. It's just for any last-minute questions or comments. Okay, so that's 5 p.m. to 8 p.m. And my office is my house. Okay, so you can check that out. This is going to be on the 14th. And I'll give you the Zoom link in my weekly announcements of things to do. So you'll have that. And those are the major things that we want to focus our attention on. Another thing I want to tell you is that this Friday we will have a new lab. Okay, so it's going to be on intermolecular forces. Actually, all of you can come to the lab, so and do it with us. So this Friday, freezing point depression. Freezing point depression is the new lab. So this Friday lab. So you want to watch the video, demonstration video. You want to read the handout. It's a little bit of a more detailed lab. It's a complicated lab. So come prepared and definitely we will help you on that. Larissa will. I may not be this Friday because I have a meeting. So freezing point depression lab. Okay, so new lab, and should be interesting. Also should be fun. What is also due is your first lab report is due. So lab report 1 is due this Friday. And that lab report is intermolecular forces. On Friday, which is 12th. Right, so turn in your lab report this Friday. Do the new lab with us this Friday. Work on your quiz. Hopefully you're doing it incrementally, I don't know, a problem a day or 20 minutes a day. Turn that in next Monday. Work on the problem sets for your exam by next Monday, and do the multiple choice for the exam by next Monday. Okay, office hours will be this Sunday from 5 p.m. to 8 p.m. Are there any questions for those here that are listening? All right, so this is our agenda. And by the way, our test 1, again, study guide will tell you what's on the exam. Test 1 will cover chapter 11 and chapter 12. All right, this Friday I'll dedicate a lecture towards a review to tell you what to study for the test. All right, so where we left off last time, I think this is the last problem for this exam, for this chapter, excuse me, and then we have some practice problems that we can go over. We left off on Monday talking about osmotic pressure. Okay, so here's the osmotic pressure equation. What is osmotic pressure? Okay, osmotic pressure is the pressure to stop osmosis. Pressure to stop osmosis. So literally we have to put something in, apply a pressure so that water doesn't rush and go through a solute. And here's the equation. I'll give you this equation on the exam. M is molarity. Okay, R is the gas constant. And then T is the temperature that is in Kelvin. So let's just go through this problem again and just finish this off. We got 0.263 grams of hemoglobin in 10 milliliters of solution. All right, this solution, remember, what is a solution? Solute plus solvent, correct? So solute plus solvent is what we call a solution. Has an osmotic pressure of 7.51 torr at 25 degrees C. What is the molar mass? Okay, so anytime you see molar mass in this problem or on your exam or your homework problems or on your MCAT or whatever future, the big, very important exams in your career, okay, you want to know that the units are going to be grams per mole. Grams per mole. And so let's use this equation here, pi equals mRT. And so we got the osmotic pressure 7.51 torr. Let's go ahead and convert that to atmospheres. So we have the atmospheres here, and that is our pressure in atmosphere. So we have to apply this much pressure to prevent water from going and running and solubilizing the hemoglobin. Hemoglobin is a main protein in the blood. So we have our pi. Okay, M is something we're solving for. Okay, this is where we left off on Monday. R is our gas constant. And then T here, we're going to convert the T to kelvins. Okay, just recapping from last Monday's class. So we solved for M, and we got 4.02 times 10 to the minus 4 big M. Okay, solving for M here. Let me box that in green or yellow. Okay, and solving for M here, we're getting this as our answer. One thing I want you to recognize, okay, multiple choice on the exam. Okay, what is big M? What is small m? Here, big M is moles over liter. Okay, many students still miss this even after taking Chem 1, even after taking Chem 2. Moles over liter. Okay, specifically, if you want to get technical, it is moles of solute, liters of solution. Okay, solution being solute plus solvent. Solution being solute plus solvent. Okay, let's not confuse this with molal, small m, which is, again, molality, moles of solute, kilogram of solvent. All right, so this 4.02 times 10 to the minus 4 molar of hemoglobin is the same thing as 4.02 times 10 to the minus 4 moles of hemoglobin HB over liters of solution. So what are we being asked to find? We're being asked to find the molar mass. All right, so we have 10 milliliters of solution, correct? All right, so 10 milliliters of solution. Let's use that here. Okay, let's use that here. So continuing on, we have 10 milliliters of solution. Okay, let's go ahead and convert that to liters. So 1,000 milliliters is 1 liter of solution. And the concentration here is 4.02 times 10 to the minus 4 moles of hemoglobin over liters of solution. So the milliliters cancel. The liters and liters cancel. So what is this on our calculator? All right, we'll just do it. 4.02 times 10 to the minus 4. Okay, times 10. Okay, divided by 1,000. It's 4.02 times 10 to the minus 6 moles. Of hemoglobin. Just because I asked Josh to open up the mini blinds doesn't mean you all can wish you can jump outside and be in the outdoors. It's like everyone's like, wish we had the sun. All right, so let's complete this problem. What is the molar mass? Okay, we got our moles here. Okay, we've got 0.263 grams, so grams over moles will give us our final answer. Grams over moles will give us our final answer, so let's do that here. So we have 0.263 grams. And we got our moles here, 4.02 times 10 to the minus 6 moles. And that's grams over moles, and that will be our answer. Right units, in the correct units, excuse me. 0.263 divided by, I like putting parentheses, 4.02 exponent minus 6, close those parentheses, grams over mole, 65,423 grams per mole. 65,423 grams per mole. And that's the that's the correct answer. You may be wondering, that's huge. That's such a huge number. It is huge because hemoglobin is a big protein. We actually study this. The biochem students study hemoglobin. I'm sure all of the PA people and the pre-meds also will know a lot about hemoglobin. It's a very huge protein. It's actually 4 subunits. It's called a tetramer. Anyway, so that's the answer to this problem. All right, I think that wraps this up for chapter 12. Here's a review. Okay, all of these are called what? Collectively, they're called colligative properties. Collectively, they're called colligative properties. The minute you add a solute to a solvent, you create, number 1, you create a solution. And number 2, all these 4 fundamental things happen. The vapor pressure goes down, your boiling point suddenly goes up, your freezing point goes down. You'll see this in the lab, hopefully, this Friday. And then for all the biology majors, you generate what's called an osmotic pressure. Okay, this happens in the presence of a membrane. Okay, in the presence of a membrane. Right, so that's page 14. What I have now on page 16, 15, 16, 17 is just practice problems, and I worked them out. Okay. Let me just talk to you a little bit about this. I will not test you on this, but what we have here is called colligative properties of electrolytic solutions. So what do I mean by electrolytic? Kind of like your Gatorade. Okay, you create a solution, but the solution goes into ions, like Gatorade or Powerade, or there's dissolved ions in there, right? So when there's dissolved ions, you have to multiply it by a factor. So everything is the same except you multiply it by a factor, and that factor is called I, more specifically the Van Hoff factor. Okay, so this happens when you have an electrolytic solution. Okay, what do you mean by electrolytic solution? Okay, ions, sodium chloride, sodium ion plus chloride ions. Potassium hydroxide, potassium ion plus hydroxide ions. So you multiply everything by I, and you look up I in a table. Okay. Everything is the same except you multiply it by I, the Van Hoff factor, and we look this up. Okay, so this is for ionic solutions, which break down into ions in water, electrolytic solutions. So for ionic solutions, everything we've done in these problems previously, except if they're ionic, we're going to multiply it by I, and we look up I in some table. And this I is called the Van Hoff factor. So that officially ends chapter 12. Here are some problems that I worked out. So, look over them, see if you can understand them. As an example, I'm not going to go over and write everything out, but to 6 grams of cyclohexane solvent, 0.060 grams of this is added. Okay, what is the new boiling point? What is the new freezing point? All right, expect to see a table. Okay, expect to see a table on any exam that gives you the freezing point constant and the boiling point constant. So we work through that problem. Again, all I'm saying is just follow through and see if you can understand the logic and flow, the pipeline to solve this type of problem. The same thing with this one. 0.85 grams of an organic compound and 10 grams of solvent benzene has a freezing point below that of pure solvent, which is 5.16 degrees C. What is the molality? Okay, so molality is moles of solute kilogram of solvent. Okay. In this particular problem, again, just look at it on your own, a little bit more meticulous eye. The kilograms of solvent here is going to be 0.010 kilograms. Freezing point below pure solvent 5.16, so the freezing point of benzene solvent by itself is 5.5. We add this 0.85 grams of organic compound. The new freezing point is 5.16. Freezing point depression. So our change is 0.34. And then we go and follow this step to get our molecular weight in grams per mole. Okay. So follow these in our notes, and these notes are on Canvas. Okay, this problem, for those of you that are going to look over the notes, here we have to solve for mole of solute. And that is our mole of solute. This is the grams that was given to us in the problem. Grams over moles is our molecular weight. And finally, an osmotic pressure problem. Benzene solution containing 2.47 grams of organic unknown has this osmotic pressure pi at 21 degrees. Again, follow the pipeline is all I'm saying. All right, so molar mass, grams per mole, that's what you want to look at as for your units. So what did we do here? We solved for M, molarity. And then we go to the next page in our notes. We got our molarity, we got this volume of solution. From there we get our moles, and then grams per mole is our final units of molecular weight. Again, instead of me going through it, you can follow the pipeline and the thought process. If you understand it, I think you'll be more than good for the exam. Okay, so just those 3 problems, look them over. And with your blessings, I'll move on to chapter 13. Is that okay? Those last 3 problems, they're worked out in your notes, so check them out. Right, Friday, we will have a review for Monday's exam, and I think in the spirit of forging ahead, I will move to the next chapter. But I do have an extra copy of the notes. Does anybody want them? Follow along. It's chapter 13. That was the last 20 minutes or so, we'll go over our new chapter here. This is chapter 13. So this is where we start getting into the nitty-gritty of Chem 2. Okay, this material here is very different that you will encounter comparatively to chemistry 1. So it's a new type of thinking, new types of variables, okay, new types of everything. So we begin this chapter with the word called rates. Okay, so what do you think the word rate means, if you were to guess off the top of your head? There's no wrong answer. So what do you think rate is? Speed. Okay, that's a good one. Yep, speed. How fast? Okay. Maybe velocity, right? Velocity. So how fast did you come in this afternoon to school? Did you speed? Okay. Did you go slow? Miles per hour you went? Okay, right? Maybe 30 miles per hour on Ramsey Street. So like that, you know, we are in a chemistry class, and we also want to talk about speed of a chemical reaction. Okay, so some reactions occur really, really fast. Okay, it's really, you can't come to school in a jet. Most of us come to school because it's too fast. Okay, most of us come to school in a car. Okay, it's some miles per hour. Some of us can come, well, some of us come to school by walking. You know, I live right here, so I could walk, but I don't. I should. And this is also not very practical, but, you know, you can come to school, you know, very, very slow. Okay. Maybe if we start at 8 a.m., we can make the 1 p.m. chemistry class. So basically, how fast? Okay, how fast a reaction proceeds. How fast a reaction proceeds. We're going to call that, as Joshua mentioned, speed of a reaction. So anytime you see the word rate, you want to think of speed. A couple of other things I want to mention to you here is speed is not in miles per hour. Okay, we're going to use concentration over time. Okay, that's our sort of assessment. Okay, I came here, you know, going 30 miles per hour or whatever, blah, blah, blah. We can't say that for a reaction. It's concentration over time. That's our speed. That is our assessment. Okay, we got to put numbers. You can't just say, oh, this reaction is fast. Oh, this reaction is slow. Okay, what do you mean? Okay, give me some numbers. Okay, so the numbers are going to be here, concentration over time. Okay, so this little bracket is what we're going to designate as concentration, and that's going to be in molar, moles over liter. Okay, moles over liter. Again, moles of solute over liters of solution. Okay, over some time t. Okay, so that's how we will assess our rate. Okay. And another thing that how we can assess our rate is, you see, let me just write to you a very generic reaction. A very simple reaction of A goes to B. Okay, the reaction A goes to B. All right. So what do you think is happening over time? What do you think is happening over time as this reaction proceeds? What do you think is happening over time as this reaction proceeds? What do you think is happening to A? Is it not dropping down? Over time, concentration here on the y-axis. Okay, what do you think is happening to B over time? Exactly, right, very good. Yeah. It's increasing over that same period of time. Okay, for this reaction to go. So how fast a reaction is going to go, can be measured by two things. how fast A decreases, or, right, are you with me? Or how fast B increases. We are actually going to go this way. Okay, how fast A decreases will tell us how fast the reaction is going to go. How fast A decreases. This will be our assessment. This will be our, measurement of how fast the reaction is going to proceed. Is it fast? Is it slow? Is it somewhere in between? Remember, we have to put numbers to this. Okay. You're on the track team, Courtney, right? Is it track? Yes, dear? Okay. So, wow, she runs fast. What does that mean? You can say I run fast, but she runs fast. We got to put numbers. Okay, we have to put numbers. You can't just say fast or slow. Likewise, we got to say the same thing for a chemical reaction. So let me give you the equation here. It's going to be rate, which is how fast. Okay, I want to introduce to you a term here called lowercase k. Lowercase k times how fast the concentration of A decreases raised to some power. I'm going to call it, I'll call it x, raised to some power x. So this is what we're going to call the rate law. Okay? The most important theme for this chapter, the rate law. So let's define some terms here for this reaction. Bless you. For this reaction. Okay, rate we know is how fast. Okay. K is something called the rate constant. Okay, lowercase k is rate constant. Let me tell you right now, I'm just going to say it out. Do I have a red pen? Yes, I do. Okay. Let's make this clear, so we'll put this in bleeding red, blood red. Okay. Okay, do not confuse lowercase k with capital K, which is next chapter. That's equilibrium constant. Okay, we see this all the time. I see this all the time, so do not confuse with capital K. Capital K. This capital K, which we will encounter in the next chapter, is equilibrium constant. So that's one of the things that makes Chem 2 a little bit hard. Not really, but do not confuse that, which is equilibrium constant K. So as they say, mind your P's and Q's, mind your K's. Okay? Lowercase k, capital K. All right, so that's for later. Lowercase k is rate constant. Concentration of A is, A is the concentration, okay, of reactant A. Okay, remember, how fast the reaction going is how fast the reactants decrease. How fast the reaction is going is how fast the reactants decrease. Okay, how fast the reaction is going, the rate, is how fast the reactants decrease. All right, this exponent x is also another complication. It's an exponent, so we raise it to the power, and it's called the order of the reactant. Order. X is the order of the reactant. All right, so X can be, what's another word for decrease? Tell me, let's play a word game. What's another word for decrease?
Depression.
What?
Depression.
Depression. more. It's the right word. You have the right letter. Right, two letters, D and E. It begins with a D and an E. Degradation. What else? Dilute is D-I, not D-E. What's another word for depression? What's another word for things going down? Decline. Descend. Okay, all of these are right, but there's that one word I'm looking for. What do they say about radioactivity? Decay. Decay. Decay is the right answer. All of those are right, but we want to look for the word decay. So this order of the reactant can be zero order decay. You got it right. Good job, Josh. One is first order decay if it's zero. Okay, so that's first order decay. And then we're going to stop at second order decay. So that's what this x can be. Okay, and we're going to, in our problems, it's going to be either zero exponent for zero order decay. It will either be 1 for that exponent for first order decay, or it can be 2 for second order decay. Now what's complicated here is that zero order decay has its own set of equations. Okay, so that's page something here, page. Anyways, you'll use this on the test. It's on page. Page 9, yeah. Page 9. So hopping and skipping to page 9. There's a whole set of equations. It's anyways this. I don't know if it's an old set of notes, if it's page 9 for that one. But you want to use this on the exam. So for zero order decay, you have your own set of equations. For first order decay, you have your own set of equations. And then for second order decay, you have your own set of equations. All right, so bring this to the exam. Okay, so we're not going to memorize it. So decay. Okay, decay is the right answer. So this is the order of the reactant, and let me just put here the word decay. So if this x is 0, then A will decay, keyword decay, with zero order kinetics. If x is 1, A will decay with first order kinetics. And if this exponent x is 2, this reactant A will decay with second order kinetics. Okay, and all of those equations in my notes are on page 9. You definitely want to bring this for your second test. Have you guys heard of the term half-life? Okay, so what is half-life? So time it takes, it's a time, so seconds, minutes, hours. If you're talking about plutonium, it's centuries, right? So half-life. So something that has zero order decay has its own half-life. Okay, something that's first order decay has its own half-life. And finally, something that has second order decay has its own half-life. Okay, so half-life. All of this has to do with decay. The decay of our reactants tells us how fast the reaction is going. Tells us the reaction rate. Right, half-life. Let me just give you my crude definition. Time it takes for a substance to decay to 50% original amount. I think that's good. Time it takes for substance to decay to 50% its original amount, to 1/2 or 50%. I mean, the textbook probably has a better definition, but, this is basically what it is. Okay, and then, again, the key word here is time. I can tell you on the exam, I'll ask what is the half-life of something something, and then they write 50, molar over seconds. No, it's just seconds. It's a time. Seconds, minutes, hours, okay, even years for some radioactive waste. So it's a time. Your units have to be in time, okay? So that's a mistake that I see a lot of students make. All right, so this is kind of what I've been telling you about previously. So our reactants are going to decay, so that's the minus sign. Your product is going to increase, so you have a positive sign here. Your positive sign, minus sign means A is going to go down. One thing we need to introduce here, going on to page 2, we're going to introduce time into this. See how much of this is happening over time. Over time. Here is A going down, and here's B going up. And again, let me write this down because this is something that you'll need to know. Rate is going to equal to K times some concentration A raised to some power A, or X or Y or whatever. So this is the main theme. What happens if you have this reaction? Okay, what will be the rate law? It's going to be rate is equal to K, okay, times the concentration of A raised to its order, 0, 1, or 2, so we have to solve for that, we'll call it X, times the concentration of B raised to 0, 1, or 2, we'll call that Y. Finally, so again, how fast your reactants decay. A plus B plus C goes to D plus E plus F. Okay, what is the rate law here? Okay, rate is equal to K times the concentration of A to the power of X. Okay, how much A you started off with, raised to its order of decay. How much B concentration you started out with, raised to its order of decay, 0, 1, or 2. That's all we'll know, or that's all we need to know, 0, 1, or 2. Times how much concentration you started out with C raised to its order of decay. Again, we're only concerning ourselves with 0th order decay, 1st order decay, or 2nd order decay. That's C. Okay. So these are all the different manifestations of the rate law. So what do you need to do? Okay, what we need to do when we do these problems is we need to find K and then find the exponent. That is our job in the problems that you will encounter in this chapter on the problems for your exam. Find K, lowercase, rate constant, and A. K is rate constant. Okay, which brings me to another complicated thing here. This is something that students also mess up on. The units of rate constant K vary. The units of rate constant lowercase k, okay, they will vary. It's not some units that you can memorize. They will change. You actually, if you have the notes, you can see here on page 9. Okay. Look at the units of rate constant lowercase k. Okay. For a, let me zoom out here, for 0 order. For 0 order, these are the units. For first order decay, the units are 1/2. For second order decay, this is 1/ms. And this is for the reaction A goes to B. Okay. So it's very complicated because the units are going to be different for each problem. Units of what? Units of lowercase k, which is the rate constant. Makes things a little bit more complicated. Okay, what is shown in brown is called the rate law. This is called rate law. So do not confuse rate law with rate expression. So this is something that's totally different. To be honest, I'm not going to ask you this on the exam. I will definitely ask you rate law, but rate expression is something that's a little bit different. So let's just go over this, realizing I will not ask this on the exam, and then we'll end class. Rate expression is basically this. So this is a reactant. It's going to decay, and it's going to decay to 1/2 its concentration over time. Okay, delta T, change in time. That decay of reactant must equal to the increase of product, water, 1/2, times the concentration of H2O over change in time, plus, equals the rate of increase of the product, O2, concentration over time. Okay. That is the rate expression. Okay, where does this minus 1/2 come from? It comes from this. Okay, where does this minus 1/2 come from? It comes from this, 2 moles. So rate of decay of this reactant must equal to the rate of appearance of this product, which equals the rate of appearance of this product. Why is it 1/2? Because you have 2 moles. Rate of decay is equal to the rate of appearance of this product, which equals to the rate of appearance of this product. This is called the rate expression, and it's something that you may encounter in your future chemistry studies. Having said that, our goal and our focus is going to be on rate law. A couple of big problems, maybe next week after our exam, we will encounter. And I think that's it. I will see you all Friday. We'll review for your exam on Friday. All right, have a good day, everyone.